We're going to finish up the note sheet for that we started yesterday. Today. Now, where we left off was absolute value and distance. So absolute value can be used to define the distance between 2 points on a number line. For instance, the distance between -3 and 4. So we take the absolute value of -3 minus 4, which is equal to the absolute value of 7, -7, and the absolute value of -7 is 7. So the distance between -3 and 4 is 7. So the distance between 2 points on the real number line, let A and B be real numbers, such that the distance between A and B is defined as this here. Now, really we can flip it either way, B minus A or A minus B. And the reason for that is because the only thing that's going to change between the two is the sign. So the one that they had before, -4 and 3, is -4 minus 3 is equal to the absolute value of -7, which is 7. Now if we flipped it, (3 minus -4), well, that's the same as 3 plus 4, which is going to give us the absolute value of 7, which is just 7. So really flipping it, all it does is change the sign, and the absolute value will take care of that. So if we wanted to find the distance between -25 and 13, we'd have -25. The absolute value of -25 minus 13. Well, -25 minus 13 is going to be -38. And the absolute value of -38 is 38. So the distance between -25 and 13 is 38. That's it. Questions on this here? So if we wanted to find the distance between 35 and -23, which one would we put first? Minus 35. Now -23 minus 35 is going to be -58, and the absolute value of -58 is 58. Now if we flipped it, 35 minus -23, well, the negative makes a plus. So 35 plus 23 is 58. Absolute value of 58 is, nope. No, because the absolute value would take care of the sign. Because the only thing that happens when we flip it is it goes from positive to negative or negative to positive. Questions on these here? We feel comfortable with these? All right, let's move on. Algebraic expressions. One characteristic of algebra is the use of letters to represent numbers. The letters are variables, and combinations of letters and numbers are algebraic expressions, like these here. An algebraic expression is a collection of letters, variables, and real numbers, constants, combined using operations of addition, subtraction, multiplication, division, and exponents. The terms of an algebraic expression are those parts that are separated by addition. For example, if we look at this one here, x squared minus 5x plus 8 has 3 terms. X squared and -5x are variable terms because they have a variable x. And 8 is a constant term because it's just a number. The numerical factors of a term are called the coefficients. For instance, the coefficient of -5x is -5. And the coefficient of x squared is 1. Because since there's not a number written in front of x squared, it's understood to be 1. Nothing too complicated so far. To evaluate an algebraic expression, substitute the numerical values of each of the variables in the expression, like this here. So if we wanted to evaluate negative 3x plus 5 for when x is equal to 3, well, we would plug 3 in for x, and then simplify. Well, negative 3 times 3 is negative 9, plus 5 is negative 4. Or if we did it with negative 1 for 3x squared plus 2x minus 1, we'd have 3 times negative 1 squared plus 2 times negative 1 minus 1, which simplifies to 0. And the same thing is true for c. We're just plugging in or substituting those values in for the variable and simplifying. And you all have done this before. Most of the time we get to highlighter. This step here, you plug it into a calculator and it solves it for you. Just order of operations. Algebraic expressions use the substitute principle to evaluate algebraic expressions. It states that if A is equal to B, then B can replace A in any expression involving A. In example 12a, for instance, 3 is substituted for x in the expression. Let's put it in another context. Well, so here our A equals B is x is equal to 3. Since B, or our 3, can replace x, each x in this statement can be replaced by 3. Now at this point here, if we wanted to simplify, we can plug it into the calculator or use order of operations. First thing we would do is 3 squared. 3 squared, 3 times 3 is 9. 3, now we can do 3 times 9. Which is 27, and 27 plus 7 is 34. Questions on this here? I don't think we've broken any real new ground. Yeah, I can go back. You're all able to remember most of this from, I think, some of this has been Algebra 2, some of this I think has been Algebra 1. Y'all have done this before. It's just new wording, new verbiage on what we're doing. We're just covering it in a different context. Basic rules of algebra. There are 4 arithmetic operations with real numbers: addition, multiplication, subtraction, and division. If you don't, that's fine. It seems like it's a lot, but it's really not. We're just restating fact. Of these, addition and multiplication are 2 primary operations. Subtraction and division are the inverse operations of multiplication and division, respectively. Because if I add 2 and then subtract 2, they undo each other. They're inverses. Definition of subtraction and division. Subtraction, add the opposite. So we could say 4 minus 2. Or I can add the opposite, which is negative 2. So I could subtract 2 from it, or I could add negative 2. Same thing, yes? And when we talked and they talked or thought about originally with negatives, they didn't think of them as negatives, they thought of them as the opposite. We're adding the opposite. But that's all that is. In this definition, negative b is the additive inverse, or opposite of b. Over here, instead of dividing, we're just multiplying by 1 over b. Is the multiplicative inverse, or reciprocal of b. In fractional form, a over b, a is the numerator of the fraction and b is the denominator. Because properties of real numbers below are true for variables and algebraic expressions as well as for real numbers. They are often called the basic rules of algebra. All of these y'all have done before. Y'all know that these are true. We just don't always refer to them by their titles or their names. The commutative property of addition. You can add any two things in any order. 2 plus 3 is the same as 3 plus 2. That's the property that states that. Commutative property of multiplication. We can multiply any two things in any order. Doesn't matter. You will get the same outcome. Associative property of addition. I can add any three things in any order. Still get the same result. Associative property of multiplication. If I multiply two things and then a third, I can multiply it in a different order. We can multiply any three things and still get the same result. Distributive property. We can distribute through and get the same result. And they are showing the top one is right distribution and the bottom is left. Or actually, sorry, it's vice versa. Left is on top, bottom is right. It's just saying that we can distribute through and get the same result. Now, that's not always true, because if you all remember last year with matrices, the order in which we multiplied left or right did change the result. So it's not always true for everything. But for us, normal polynomials, what we're going to be dealing with, it is true. The additive identity property. If you add 0 to something, it doesn't change it. I think that was one of our favorite ones in elementary, wasn't it, adding 0? The only one that we liked more than it was multiplying by 0. So it gave us 0. Multiplicative identity, multiplying by 1, gives us what we have back. Additive inverse property, if we add the opposite or the negative of what we have, we'll get to 0. And if we multiply by the inverse, we get 1. If subtraction is divided as adding the opposite, the distributive property is true. Yep. And again, all of this is just more properties. The negative, 0, addition, subtraction, divide, factor. So nothing really new. A prime number is an integer that has exactly two positive factors, itself and 1, such as 2, 3, 5, 7, 11, going on. 1's not prime because it can't be itself and 1. So they exclude 1. The numbers 4, 6, 8, 9, and 10 are composite because they can be written as the product of two or more prime numbers. Fundamental theorem of arithmetic states that every positive integer greater than 1 is a prime number, or it can be written as the product of prime numbers in precisely one way, disregarding order. So either it's going to be prime, 1 in itself, or a product of prime numbers. That's it. So, 7, 8, yes. 7 and 8, in this exercise, determine which numbers in the set are natural, whole, integers, rational, and irrational numbers. So it's not going to ask for real numbers to be listed, because if that were the case, it'd be all of them except for I. 7 and 8. 11 and 13. Plot the real numbers on the real number line. So for, 11, sorry, not 11, 13, just 11, you're going to draw a number line and plot the 4 points. 13, 14, plot the two real numbers on the real number line, then place the appropriate symbol between them. So you're going to plot them on the number line and then say which one's greater or less than. 17 through 22. You do not have to give a verbal description. Sketch the subset on the real, so for 17 through 24. All you have to do is sketch them on a number line, sketch the inequality on a number line, and then state where it's bounded or unbounded. Again, bounded has two endpoints, unbounded does not, it only has one. 29 through 45 odd. So 29 through 37 odd, evaluate the expression. Yes. 39 and 41, you're just putting the appropriate symbol, less than, greater than, or equal to. 43 and 45, find the distance between the 2 points. Because we talked about that briefly today, I can put that back up if we need. Then 53 through 63, odd. 53, 55, or 57, identify the terms. Then identify the coefficients of each expression. Yep. 59 through 63, odd. Evaluate the expression for each value of x if possible. Sorry, evaluate each value of x. If not possible, state why. State why you couldn't find the value of x. And that's it.